For centuries, people have wondered, could there be intelligent life beyond Earth? Finally, science has developed the means to find the answer. The methods include sophisticated computers, some unusual ideas of how a message might be sent, and an assist from science fiction. Their goal? To answer one of humanity's oldest questions. Is anybody out there? With host Lily Tomlin. Tonight on Nova.
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
Say, you ever wonder what goes on when the theaters close, when no one's watching? What I think, that's when the space visitors show up. I mean, they think we're a little weird, so they're shy, you know what I mean, in the day. That's why you don't see them, unless you know how to communicate. Hey, I mean, you gotta admit it's likely. There's all kinds of beings all over the solar system, don't you? The way I see it, we can't be the only things going, can we? And that must mean that they're all over the galaxy.
For thousands of years, people have been looking at the skies, wondering what might be out there.
Hey! It's moving!
Hundreds of science fiction films have depicted what happens when there's a failure to communicate.
Everybody understands when you wave the white flag, you want to be friends?
During the 1950s, at the height of the Cold War on this world, many classic science fiction films suggested there was no reason to figure out how to communicate. The aliens were implacably hostile, and the sooner they were gone, the better. By the 1970s, contact, not conflict, became the theme of the most successful science fiction films. The characters in these films try to communicate in pure tones, a language that they think might be universal. Movies like Close Encounters of the Third Kind and E.T. the Extraterrestrial reflect and shape our changing concepts of the universe and the beings who may inhabit it. And in fact, they just might help determine if and when we humans make contact with real ETs.
Hello, I'm Lily Tomlin. Recently, I was on Broadway playing Trudy, a bag lady who receives extraterrestrial messages through her umbrella hat. It's kind of primitive, but for Trudy it works. I like to think of her as someone who lets her imagination overpower the reality that surrounds her. But this program is about the real thing, how we might contact alien civilizations, not in our imagination, but in actual fact.
– 2 a.m., September 24th, 1985. In a physics lab at Harvard University, Earth's most sophisticated detector in the search for life in space is put to its first real test.
Oh, that's a beat. What is /n, small n?
In the tradition of hackers and inventors everywhere, Professor Paul Horowitz and his student Brian Matthews burn the midnight oil.
Chunk. Okay. Big program. How many lines is this thing?
It's been weeks of late nights to ensure something happens when the system is switched on for the first time 5 days later.
Okay, this is going to be at 20.4 kilohertz off of DC. Say when?
Not yet. You got to download code version. Set. Go.
Now, is that running?
Oh, crud.
I don't know if...
Okay,
Brian, I don't...
This may seem like a shoestring effort, and it is. But previous efforts have been less specialized, using receivers not custom-made for the search.
Pretty good with it. Well,
What sits here in the lab, stripped to its silicon guts, is only half the system.
Okay. It now says start and start
we
frequency.
got a nice big signal.
So I'm making a chirp, and you're looking for a chirp. This is the real thing.
Data.
Soon it will be linked to a large radio antenna, and the search to detect a signal from an alien civilization will begin.
Okay, it's only 2 channels wide.
Scientists have known about radio since the start of the 20th century, but only in this decade have advances in computers provided tools powerful enough for SETI, the search for extraterrestrial intelligence.
Okay, great. So we've run it all the way through the system. A synthesized chirp is detected as a synthesized chirp at this end, and it tells you exciting messages on the screen.
5 days later, September 29th, astronomers gather at a radio telescope near Boston. For the ceremonial switching on of the detector, Horowitz had scrounged up a knife switch from a derelict laboratory, and inside was still making last-minute fixes. He calls the system META, short for Mega or Million Channel Extraterrestrial Assay.
3 or 4 parts in 10 to the 10.
Some of the scientists most interested in SETI came to the ceremony, including astrophysicist Philip Morrison, who first proposed, some 25 years ago, the basic methods META uses to listen for other civilizations. The member-supported Planetary Society funds the operation of META, with the help of a donation from movie director Steven Spielberg, who created E.T. and Close Encounters.
When I was your age, we had rabbit ears on our TV set.
An even more powerful detector than META is now under design by NASA. These SETI experiments may fail to make contact with real ETs, but scientists want to go beyond our movie fantasies and communicate with another civilization.
Well, I'm very happy to be involved in this project because, as you all know, I've benefited so much from science fiction. I just thought it was time to get involved in some science reality. I just hope that there is more floating around up there than just old reruns of the Jackie Gleason show. Okay.
Among the scientists who have helped SETI grow from pure speculation toward legitimate science is Planetary Society President Carl Sagan.
Cheers. May it find something. There is some chance that in the next few decades we will get a signal from some spectacularly distant, spectacularly exotic civilization, and everything on Earth will, as a consequence, change. That is possible.
If other civilizations are out there, where are they? Why aren't they here? After all, we humans are space travelers. Wouldn't any civilization advanced enough to send a message come to Earth in person, like Spielberg's E.T.? In reality, space visitors would have to come a very long way, for we on Earth seem to have no close neighbors. The Viking spacecraft touched down on Mars and found no clear signs of life. Other spacecraft have found no evidence of advanced beings on any other planet in our solar system. The Voyager 2 spacecraft is the fastest vehicle ever built by humans, but it still took 9 years to reach the planet Uranus, just over halfway to the edge of the solar system. To find another advanced civilization, we must look to the stars and any planets that surround them. But Voyager would take 100,000 years to reach even the closest stars. Barney Oliver, head of NASA's planned SETI project, thinks aliens would be daunted by these realities.
I think they're smart enough not to travel. I think when you compare the costs of interstellar travel with interstellar communication, they, like us, would choose interstellar communication. It's far cheaper. It's cheaper by billions of times.
So if we have to expect distant, not close encounters, what's the best method of communication? That depends on who you're trying to talk with and where they live. In the 19th century, some scientists still believed our solar system was teeming with life. They assumed that beings on other planets would be studying Earth carefully. In 1833, a German mathematician, Karl Gauss, suggested planting in Siberia a huge triangle of wheat bordered by dark green pine trees. Alas, for devotees of environmental art, Gauss's project was never funded. Nor was the idea of Johann von Littrow of Vienna, who suggested digging geometrical shapes in the Sahara. Von Littrow wanted to fill the trenches with kerosene and to set them ablaze to make a glowing beacon on the night side of Earth. In fact, these bizarre schemes might well have worked if aliens had existed on the Moon, on Mars, or Venus. But methods of communication that work over interplanetary distances have no chance at all between the stars. Distances between the stars are so enormous that astronomers measure them by the velocity of light, the fastest speed in the universe. 1 light year is the distance light travels in a year, 6 trillion miles. Our galaxy, the Milky Way, is 100,000 light years across. The galaxy contains an enormous number of stars and a vast potential for other civilizations. Skeptics say that advanced civilizations would surely have made themselves visible, but as yet we have seen no evidence of life out there. So, what scientific reasons justify continuing the search? In 1960, Frank Drake made the first radio search for civilizations in space. Drake's experiment produced some exciting false alarms, but no real messages. For over 25 years, Drake has kept on looking. What does he think we might learn?
Oh, the most important information by far would be just the simple fact that they exist in space. That will tell us that civilizations like ours can thrive for long periods of time, that they can overcome the threat of nuclear war, that they can preserve their environment, that they can maintain high technology and a high quality of life. And all of that, I think, is very important for us to know.
Drake called his pioneering search Ozma, after a princess in the fictional land of Oz. He said SETI also deals with faraway lands, difficult to get to and populated by exotic beings. But maybe SETI itself is just as fanciful as the land of Oz. Drake argues that what we already know, plus what we have good reason to believe, justifies the search. He came up with a way to organize our knowledge and our ignorance, to give some substance to our speculation. Scientists call this the Drake equation, though you don't need an A in algebra to understand it. The Drake equation presents 7 conditions astronomers think necessary for the existence of a civilization which could send a message to us. If you make an estimate for each of the terms and multiply them all together, you end up with an informed guess about how many advanced civilizations are out there. The larger that number, the easier to establish contact. The first term in the equation is the number of stars in the Milky Way. Of all 7 terms, this is the only one we know with a fair degree of accuracy. By observing other galaxies as well as our own, we estimate that the Milky Way contains about 400 billion stars. Second, how many planets might orbit these billions of stars? We don't have clear evidence of any planets outside the solar system, but with much improved technology to help in the detective work, the hunt for planets is on. In 1985, Rich Terrestrial of NASA's Jet Propulsion Laboratory was co-discoverer of a faint disk of material surrounding the young star Beta Pictoris, about 50 light years from Earth. This may be humanity's first glimpse of another solar system. The disk of material may be about to form planets. Some scientists argue that, like our sun, the majority of stars have planets. The third term in the Drake equation asks, how many planets or their large moons would provide an environment suitable for life? In our own solar system, we have found no evidence of life on the airless, waterless moon, nor on broiling Mercury, nor stifling Venus, nor in the swirling clouds of Jupiter, nor beneath the majestic rings of Saturn. But some scientists believe that Mars was once more habitable. They point to its polar caps of ice and to riverbeds that channeled liquid water a billion years ago. They look at Jupiter's large moon, Europa, and wonder about possible life beneath its frozen crust. They yearn for a future mission to pierce the clouds that shroud Saturn's moon, Titan, where conditions may resemble those on Earth at the time when life arose. In a solar system with some 20 worlds, 1 hit and 3 near misses, an optimist like Drake might say, implies that many planets may be habitable by some forms of life. The fourth question is, on how many of these suitable worlds does the complex process of life actually begin? In a now famous experiment, Stanley Miller and his colleagues took a first step toward answering this question. They tried to create a dynamic model of the Earth as it was 4 billion years ago. The flask was meant to represent conditions on Earth before life appeared. They mixed in simple chemical compounds and used sparks to simulate lightning or the sun's energy in the early atmosphere. The simple molecules broke apart and then formed more complex compounds. 4 billion years ago, these compounds would have rained into the seas of the primitive Earth, where they could have formed even more complex molecules, such as glycine, one of the amino acids, the basic building blocks of life on Earth. Scientists have also found amino acids in some of the meteorites that have fallen to Earth from space. These amino acids apparently formed in an environment even more hostile than that of the primitive Earth. From simple organic molecules to a living reproducing organism like us, controlled by DNA, is a huge step. But the most basic building blocks of life appear to be common throughout the universe. The fifth term in the Drake equation asks, how many worlds nurture not just life, but intelligence? We know that on Earth, simple forms of life have gradually evolved to become intelligent life, able to manipulate the world around them. The survival value of intelligence may be so high that intelligence arises wherever life emerges. But for now, we just don't know. The sixth term is the fraction of planets with intelligent life on which emerges a technologically advanced civilization, which we can arbitrarily define as one that knows how to use radio. On Earth, we're batting 1 for 1 on all these terms, but on other worlds, the most advanced forms of intelligent life might be rather like whales or dolphins, and may never develop this sort of technology. Even if there's a lot of them out there, we can't hope to communicate with them across interstellar distances. Does advanced technology carry with it the seeds of self-destruction? The seventh question, the average lifetime of a technological civilization, cannot easily be answered until we succeed in SETI. If many civilizations flower briefly and then disappear, only a few can be sending messages at any one time, and SETI will be difficult, if not impossible. If you ask scientists for their best estimates for each of the terms in the Drake equation, you find a wide variety of opinions, even on the factors we think we know fairly well.
Few hundred billion.
All right, gentlemen, how many stars are there in the Milky Way galaxy?
There are 200 billion stars in our galaxy.
About 200 billion stars in the galaxy.
Everybody agrees about 100 billion stars in the galaxy.
Well, I think probably about 400 billion or so.
Few hundred billion.
Now, how many planets are there per star?
We believe that there are about 10 planets in each planetary system.
Be about 10 planets per star.
I think about 8.
1 star in 10 might have planets.
Several per star.
So, how many planets per star are suitable for life?
1 or 2 planets.
One. Perhaps 1.
At least 1 per system.
Let's get more speculative. On how many of the worlds that are suitable for life does life actually begin? To save time, just the most optimistic and pessimistic estimates, please.
I would guess that it's pretty close to every suitable planet.
It's basically a sheer guess. My guess might be, say, 1 in 10 to the 8th, just because 8's my lucky number, and not for any better reason than that.
10 to the 8th? 1 planet in 100 million? Okay, so what's the chance of life becoming intelligent?
It now looks more and more as though every system of living things, given a few billion years, will produce an intelligent species.
And again, because 8's my lucky number, I choose 1 in 10 to the 8th as my guess on that factor.
And on how many worlds would intelligent beings develop the technology to communicate between the stars?
On every world where intelligence develops, it is likely that given enough time, technology also will develop, and with it, the ability to communicate across space.
After intelligence forms, I think perhaps a 1% chance of radio communication.
Now, gentlemen, here's the big question. What are your guesses, no more than guesses I know, for the shortest and longest average lifetime of a technologically advanced civilization?
I think there's a threshold here. I think if a civilization crosses a technological threshold, then that time could be measured in millions of years. If the civilization doesn't attain that threshold, then I think it could be tragically short, perhaps as little as 50 or 100 years.
I think it will be billions of years, basically, the full main sequence lifetime of the star. I can't imagine that an advanced civilization would somehow self-destruct or let itself be destroyed.
So what's the bottom line? On the optimistic side, Frank Drake says that there could be at least 10,000 technologically advanced civilizations in the Milky Way alone. Remember that the larger the number of civilizations, the nearer to us our closest neighbor might be. On the other hand, Ben Zuckerman's pessimism would lead us to conclude that no other civilizations exist in the Milky Way, and possibly not even in millions of other galaxies around us. With this wide divergence of opinion, how useful is the Drake equation?
I mean, nobody takes these numbers to be tremendously serious. Nothing depends on there being 1 million civilizations as opposed to 1 billion or 1,000. The only question is, are there many, or are there very few, or are there none? And as long as there is a plausible argument for many, we ought to keep looking. I think even if there's a plausible argument for a few, we ought to keep looking. I'd even go further than that. If there's a plausible argument that there isn't anybody out there, bearing in mind that we can be wrong, we ought to keep looking, because the question is of the most supreme importance. It calibrates our place in the universe. It tells us who we are. And so it is worthwhile trying to find other civilizations, I would say, no matter what.
Since these pessimistic and optimistic estimates are simply the results of multiple speculations, experimenters such as Paul Horowitz aren't willing to stop there.
People have argued for a long time about the odds. What are the probabilities that there's life elsewhere in the universe? What are the probabilities that life is sending signals to us? So it's pretty easy to come up with arguments that make it semi-probable or highly improbable. And lacking any data, they're nothing but arguments. And you can argue yourself blue in the face. But if you want to answer this question, you're going to have to do the experiment.
Modern equipment is essential, but SETI involves more than electronics and computer wizardry. Making contact means you have to consider the technology, psychology, and biology of whoever might be on the other end. First, where and when to look.
A gracious hello, Ernestine's message service. You stay in touch because we care so much.
Messages for Green?
Mr. Green? Oh, good. Your rich uncle, Mr. Pursewarden, did phone. He said that he would call back once more before he goes on his cruise to tell you how he's coming to town. He said you must stand by, as you will not be able to reach him once he's gone. I did my part. EMT. Oh, Miss Pinckney, yes, of course. A conference call at 5 with Mr. Wright and Mr. Bright. Do you happen to have their numbers?
You should have their numbers.
Do I have their numbers? If I did, would I be here? EMT. Oh, Mr. Pursewarden. Oh, yes, sir. I am ringing your nephew. 2 ringy-dingies. 3 ringy-dingies. I'm sorry, there's no answer.
Did you give him my message?
I did tell him to stand by, sir.
Well, tell him I'm
Very well, I will tell him, and what a pleasure talking with you. EMT.
Jones here.
Yes, Mr. Jones, the 6 p.m. meeting is now at 7 for 6. That's what I said. There's nothing really hard to understand about that, Mr. Jones, if you just concentrate. EMT. Yes, Mr. Green, your uncle, Mr. Pursewarden, did call. I don't mean to pry, but just where were you? Oh, really? Well, when I say stand by, I mean by the telephone. Well, I don't know. Let me see. What did he say? He's coming to town next month, and if you don't meet him, you're out of the will. No, he didn't say how he's coming, Mr. Green. No, I don't know if he'll call back. There is no need to yell at me, Mr. Green, just because you're a little confused. Yes, I suppose it is a little intelligence test for you. Just figure out where to meet him and stay there. Why don't you try the big clock at the station? Or maybe the airport. I think we can forget the bus depot. Yes, I'm sure that he meant this town, don't you, Mr. Green? Mr. Green, if you're going to shout, I'm going to give your plug a yank. I know he has millions. Very well, sir. I understand. No calls until you figure it out.
In SETI, we're in even worse shape than Mr. Green. We don't know if there is a rich uncle, let alone when or where he wants to meet. Can we even figure out how a message might be sent to us? Consider a great canyon here on Earth as a metaphor for the chasm of space and time between the stars. Suppose you're on a camping trip and think that someone else might be out there, somewhere in the same hills. You want to get in touch, but how? Suppose on the other side of the canyon, that someone also wants to communicate. Just by looking, there's no sign at all of anybody out there. But one thing's certain about communication on Earth or in space. Some methods work better than others. Suppose you realize that a Star Trek is impractical. In your frustration, you come up with an alternate strategy. Sending a message by unmanned probe might seem preferable. We humans have put slightly more sophisticated messages aboard the Pioneer and Voyager spacecraft. Still, there's the question of how much energy you can deliver. And space is awfully big in comparison to an interstellar probe. Maybe sending particles of matter, even small ones, isn't the best idea. Suppose you try sending messages by waves. Hello? Sound waves, for instance. If you did, you might discover that different frequencies have different characteristics. As every school child knows, at a distance, a low-frequency shout attracts your attention less than a high-frequency whistle. But the most piercing whistle won't be heard even a few miles away. Well, life must go on. You need warmth and light. A camper, like a civilization, may do things for his own purposes that could be visible across the cosmic canyon. You might not even realize that you've stumbled on a means of communication. Across the canyon, the flames might be seen, but thought to be a brush fire, a natural event, not a beacon. There's no sign of intelligence just in a fire, but it might give you an idea. Suppose you build a fire, but modulate, to use the SETI term, or manipulate the puffs of smoke. Now you're talking. You're sending a clearly artificial signal that travels at the speed of light and is visible for miles. But if the laws of Murphy, as well as those of Einstein and Newton, hold true throughout the cosmos, then even your best idea may fail to establish contact. One civilization may be asleep when the other is sending. But suppose you were given a method of communication common to both sides of the canyon. Suppose it was fast, cheap, and efficient. Call it radio. It might seem that your troubles were over once you've learned to turn on and tune in. But in fact, your work is just beginning.
Hello. Channel 1, it's too obvious. Channel 2. Hello?
Even with just 2 channels on a primitive walkie-talkie, it takes time to figure out how and when to speak or listen.
Channel 1. Hello? Hello?
Successful communication requires mutual agreement on how to communicate. In SETI, an unspoken agreement must somehow occur without a meeting. For all these difficulties, most SETI scientists think radio is the way to go. You can see why if you look at how well signals of different frequencies can be recognized across vast distances. Light and radio are both parts of the electromagnetic spectrum. Light differs from other kinds of electromagnetic radiation in its frequency, the number of vibrations per second of each wave of light. Light itself comes in many different frequencies, which we call colors. Red has the lowest frequency, blue a higher one. All the colors of light span only a tiny part of the electromagnetic spectrum. At infrared frequencies, below those of visible light on the spectrum, the black but still warm campfire glows brightly. So does the sun in the sky, and the trees, the bushes, and people on the surface of the earth. At still lower frequencies, we observe the scene in radio waves. The sun is only a weak source of radio, but the Milky Way galaxy in the sky on the left is a strong one. Artificial sources of radio, like our camper's walkie-talkie, stand out brightly because the Earth has almost no natural radio sources. The same principles apply in the heavens. In visible light, the sun outshines the Earth by more than 1 billion to 1. That's one reason we haven't been able to detect planets around other stars with even the largest optical telescopes. It's like trying to see a firefly perched on the rim of a searchlight. In infrared, even the dark side of Earth glows. The Milky Way forms a bright band across the sky. But it's radio that gives Earth its unique signature as the home of intelligent life. At certain times and frequencies, the Earth outshines all other sources within the solar system by nearly 1 million to 1. These radio waves also make Earth stand out to distant civilizations.
You ever wonder what goes on when the theaters close, when no one's watching?
The program you are watching is an embryonic interstellar message. 33 minutes after this broadcast began, our opening sequence has traveled 370 million miles and has nearly reached the orbit of Jupiter. Some of the radio waves that carry TV broadcasts leak into space and form a spherical shell around our planet and its sun, expanding at the speed of light. 3 hours from now, this program will overtake Voyager, 2 billion miles from Earth. Voyager has been traveling for 9 years. If in our imagination we could travel much faster than light, we could overtake our radio and TV broadcasts. 4.5 light years from Earth, we might find news of the wedding of Prince Charles and Lady Diana, passing the sun's closest neighbors, Alpha Centauri A and B. Any planets around the star Altair, 17 light years from Earth, are now receiving our news from the late 1960s.
Houston, you're go for landing, over. 1201, roger, 1201 alarm. 1201 alarm. Same time, we're go. It's one small step for man, one giant leap for mankind.
If they had sensitive enough detectors, they could watch as we became a spacefaring civilization.
Because I have a dream.
Any beings on planets around Fomalhaut, 23 light years from Earth, might see evidence of humanity's nobler aspirations.
They will not be judged by the color of their skin, but by the content of their character. I have a dream.
Planets near Arcturus or Pollux, each about 36 light years from Earth, might pluck from the cosmic background shows from the early years of television before Jackie Gleason was in reruns. Aliens might not share our sense of humor, and in reality, they might find it hard to decipher individual programs, but there's still much to be learned. As the Earth turns, TV, military radar, and microwave signals appear and disappear over the horizon, flashing like a cosmic lighthouse. As a guide to what we might someday learn about another civilization by eavesdropping on its unintended signals, astronomer Woody Sullivan has studied what our radio transmissions reveal about Earth.
And we found that you could get the Earth's spin rate, you could get the size of the Earth, you could put together the map of where the television stations are located on the Earth quite easily. You could get the size of the Earth's orbit and the length of time it takes for the Earth to go around the sun. You could get the temperature of the Earth from basic physical principles. And think about the difficulty of trying to purposely send a bit of information such as the temperature of the Earth. Whereas here it falls out in a pretty natural manner.
What about a message deliberately beamed toward us? There may be a clue to its contents and how we might decipher it in the single message we on Earth have intentionally sent into space. The Arecibo Radio Telescope in Puerto Rico is the largest single collector of radio waves on Earth, but it can also transmit. In 1974, 14 years after Ozma, Frank Drake used the Arecibo dish to beam a signal toward a distant cluster of stars. The signal was a stream of on-off pulses, shown here as zeros and ones, 1,679 pulses repeated several times. An alien civilization might consider the signal meaningless unless it realized that 1,679 is the product of two primes, 23 and 73, numbers that are divisible only by themselves and 1. The language of mathematics may be universal, so they might hit on the mathematical device of arranging the ones and zeros into a pattern of 23 columns and 73 rows. If they darkened the ones, they'd begin to see a picture. They would see a crude representation of the beings that sent the message. A map of our solar system with Earth singled out. A diagram of the Arecibo dish. And the all-important DNA molecule. The Arecibo message was beamed toward a star cluster in the constellation Hercules, 25,000 light years away. 50,000 years from 1974, and about the year 51,974, humanity could receive a reply. At a symposium held to celebrate the switching on of Meta, Carl Sagan and others discussed whether we should be sending messages or listening. They argued that waiting for a reply takes a little too long.
Because if you send, you know darn well you're going to have to wait a round-trip travel time, at least 10 or 20 years. Experiments that take 10 or 20 years are intrinsically less interesting than ones that might return an answer tomorrow.
And that's a very optimistic number, 10 or 20 years. Even the most optimistic estimates of the distances to the nearest civilization generally come out to be hundreds of light years away, which would mean that if you were saying hello to a lot of guys, it would be, 2511 or something that the message would get back, and be a little disappointing for you personally to take that long.
What might a message arriving here on Earth say? What would we like to know?
Like perhaps a cure to some of our own human ills, like cancer or pollution or the gradual loss of our resources and stuff like that.
I think with all the scare that science fiction puts into the public's minds of these monsters and creatures that want to take over our planet, I think that a friendly message would make everything worthwhile.
And I hope that they can teach us a little bit about how to handle all the technology that we're dealing with now, and teach us about how we can prevent the environment from being ruined.
Most SETI scientists have a rather different perspective.
What I would like to know is an answer to a very simple question. Are we alone as conscious beings in this entire buzzing 400 billion star galaxy, one of 10 to the 10th other galaxies? It seems pretty implausible.
Phil Morrison thinks that the signal itself would intrigue scientists, but that the public would have different interests.
It'll be a sensation when it's confirmed. In fact, it'll be quite a sensation before it's confirmed. And then it'll turn out to be false. And then finally it'll be confirmed, and that'll be a sensation. It'll occupy the front pages of all the newspapers for a week. And it'll occupy the inside pages for another month. And then it'll occupy a weekly piece every once in a while for 6 months, and that'll be the end of it. But then scholarship and interested people will grow up everywhere, fascinated to hear the latest, and they'll demand other receivers being built everywhere. All countries will pretty soon have them, and they'll all be pooling their stuff. A whole branch of knowledge will go in. The existence of signal will be all we know for a while, and then, of course, where it's coming from, and then 1,000 speculative authors will arise to say what they look like and who they are, and so on, all of which will be false. And then gradually the truth will come out. But you know that the television cameras will come the very next day and say, now, what do they look like? And do they speak English? And a number of other questions.
So, if radio is the medium of choice and listening is our best strategy, does this make contact easy? Is it enough to turn on our radio detectors and wait? Well, not exactly.
A gracious hello, ET&T. Ernestine Tomlin atop the transmitter. Let's see what's on the radio, Daddy-O. Oh, yikes, 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 there's that crazy radio beacon again. Oh, aggressive bunch of jokers in that galaxy. Too bad no one listens to that frequency, you fools. They broadcast 1 minute every 1,000 years. Just how long do they live? Try 1420 megahertz and keep doing it. Oh, those nudniks. They think they're so great with their zeta waves. What a shame no one else has discovered them yet. If they just think archaic, they'd get an audience. Oh, there's that catchy tune. Da, 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 da. Oh, I do love that fat guy and that Norton. Must be a real fun planet down there. Too bad it's so far away. What a great job. These life forms are so fascinating, but of course none so much as I.
Ernestine is grappling in her usual efficient manner with the many problems that remain for SETI scientists who have chosen radio. What kinds of signals to expect, blips, pulses, or sustained waves, when to listen, and where, and above all, how many frequencies to monitor. An ordinary FM radio dial shows frequencies in megahertz, or MHz, meaning 1 million vibrations per second for the radio waves carrying the broadcast. To avoid interference, we on Earth license radio stations to a channel, a small range of frequencies, like those around 89.7 megahertz. But the cosmic radio dial is very different. In cosmic reality, the region between 90 and 92 megahertz can contain not 10, but 20 million different channels, each of them capable of carrying a message from another civilization. With a conventional radio receiver, the finely tuned signal would be lost in the sea of background noise. Not only must the cosmic radio dial be sliced much finer, it's also much longer. On the cosmic dial, the region from 88 up to 108 megahertz contains about 200 million potential channels. And FM is just a tiny part of the spectrum. Below FM are frequencies used for some TV broadcasts. Higher than FM is UHF TV, then microwaves. The radio spectrum technically extends all the way down to zero frequency. With this enormous range, how can we possibly figure out what frequency an alien civilization might choose? Is there any way to limit the search?
There is a preferred region in the electromagnetic spectrum, we believe, that minimizes the energy required to make contact, and that is in the microwave region. And the reason for that is that the noise that would interfere with our transmissions, or theirs, is lowest there.
If we map the interference, we find that the low frequencies, shown at left, are useless because of the radio noise of interstellar space. To the right, our atmosphere absorbs the higher frequencies. In the middle lies the preferred region, from about 1,000 to 10,000 megahertz. Even so, there are about 100 billion potential channels here. Are there any other clues to help narrow the search? One basic fact about the universe is that hydrogen is the most abundant atom. In their constant dance of energy capture and release, hydrogen atoms naturally emit radio waves at one particular frequency. They broadcast at 1420 megahertz. That the universe itself might tell us where to look in frequency was first proposed by Philip Morrison. At the symposium on Meta, he reasoned that intelligent beings everywhere could reach unspoken agreement.
This is an anti-cryptological game, a game where the rational transmitter says, I want to make it as easy as possible for those distant primitive folk to get onto this channel and begin to see how it goes. And therefore, I will not conceal it. I will make it anti-concealed. I'll make it as self-transparent, as self-justifying, as visible as possible. Given the
Betting on a magic frequency, such as 1420 megahertz, helps to simplify the task of sifting the cosmic haystack. An alien civilization might broadcast a powerful signal at just this magic frequency, hoping it could be detected above the heavy background noise from all the hydrogen atoms. Drake's Ozma search used 1420 megahertz to scan 2 stars for 400 hours. His receiver could cover only one channel, as if you had a radio that could only be tuned to a single station. A search called Ozma 2, made by Ben Zuckerman, looked at 674 stars also around this magic frequency. And Horowitz in Meta is still essentially playing the magic frequency game. Unlike the Ozma searches, which looked at individual stars, Meta is a sky survey. Meta's antenna sweeps out a beam across the entire sky, about the size of the full moon. In 8 months, Meta surveys the entire sky visible from the observatory. When one survey is complete, Meta can begin another, at a different magic frequency. But astronomers have come up with more than a dozen magic frequencies. And because the Earth and any source of radio is always moving, any signal will drift in frequency over time. So SETI detectors must be able to scan many channels or groups of frequencies.
Big Daddy here, this tower of computers.
Drake's Ozma detector had only one channel, 1/10,000th of a megahertz wide. Horowitz's system scans 8.4 million channels. It can do in a second what would have taken Ozma 5 years.
This complete array here, therefore, functions as an 8.4 million channel receiver. And by the way, not like a police scanner where you do one channel after another sequentially. This receiver box here is like 8.4 million radios all sitting on the table, all tuned to successive stations. It analyzes them all simultaneously. This was actually designed.
Despite this tremendous progress, Meta still covers only an extremely small part of the radio spectrum, but it is perhaps the ultimate magic frequency machine.
It all together. From this array, which will be the first thing to know if a signal's come in, the information passes to this controlling computer here. This computer really rides herd over the whole system. It downloads the instructions to all of these different processors, keeps track of the motion of the Earth with respect to the signals that we're looking for, and looks for possible signals of extraterrestrial origin. When it finds something, as it may have done here, it will do several things. It archives interesting, unusual, large peaks that may be extraterrestrial intelligence, and if the signal is really interesting, it turns on a tape recorder. Actually, a friend of mine came and looked at this the other night, and he said, Horowitz, the reporters are going to say, show us what it would be like if a signal actually came in. And so I said, well, we can do that. We can turn on an oscillator. And he said, well, what does it do then? And I says, well, it'll say large peak. I said, it will say large peak. And he said, no. He said, have it say, notify operator immediately, possible signal of extraterrestrial origin. So that's what we're going to have it say.
No such signal of extraterrestrial origin has been detected in the year Meta has been operating.
We have hardly begun to search the great cosmic haystack. We've hardly searched all the various frequencies, the forms of signal, the places in the sky from which signals might come. And so the fact that we so far have no evidence of extraterrestrial life is not at all discouraging. We shouldn't have found it yet. We have hardly begun.
In the heart of California's Mojave Desert, NASA researchers are testing prototype equipment specially designed for a far more comprehensive search. The site is the Goldstone Tracking Station, the main downlink for NASA's interplanetary spacecraft, such as Voyager and Pioneer.
We're looking for a signal now that's coming from the Pioneer spacecraft, which is now outside the solar system. It's beyond the orbit of Neptune at a distance of about 3.5 billion miles. Its carrier is a 1-watt signal And that is about 1/20th of the energy of a candle burning. So we're picking up a really small signal indeed, if we succeed.
Though it's difficult, finding the signal from Pioneer is much easier than detecting the beacon of an alien civilization.
Let me note this down and have him turn his signal on again. Let's make sure we can get it.
The signal is weak and drifting in frequency, but it's very close.
I have to go to 333-147.
This test is only a tentative tryout for the real thing, challenging the computer's ability to recognize an artificial signal in a sea of radio noise.
2291.
And this one is 874, right?
Really?
2291874.
That's wrong. It clearly is
Gotta
wrong.
be wrong.
The NASA effort has united Barney Oliver and other longtime SETI proponents with a younger generation of computer builders and programmers.
Just let's see what happens, Peter.
Slated to last about 10 years and to cost around $100 million, SETI is one of the least risky and lowest cost items in NASA's portfolio. They hope to be funded by 1988.
Yes, I think that's it. This bright line you see going slanting down the screen is the signal from the Pioneer 10 spacecraft.
The NASA team plans to avoid reliance on magic frequencies and to search the entire favorable region of the radio spectrum. By distinguishing different types of signals over a wide range of frequencies, they say they will cover millions and maybe billions of times more possibilities than all previous searches. NASA will use existing radio telescopes and equip them with new sophisticated signal processors. SETI Deputy Project Manager Mike Klein describes NASA's two search strategies.
And they're complementary. One of them is called the Sky Survey, and another is called the Target Search. And the objective of the Sky Survey is to search the entire sky, making no guesses as to what are the best directions. To carry out that search in a reasonable length of time, we have to do it quickly, which means we sacrifice sensitivity to signals. We only detect maybe the strongest of the signals that might be there.
NASA's Sky Survey will cover a frequency range 20,000 times wider than Paul Horowitz's META. To cover the sky quickly, it will drive the radio antennas far more rapidly than usual, so rapidly that researchers are worried that the telescope mountings may be overstressed by the motion.
The complementary approach is to say, let's concentrate on detecting with more sensitivity, be able to detect weaker signals, and to do that we look in a few directions for longer periods of time, and that's called the targeted search. And we pre-select a set of stars that we know a priori are more or less similar to our own sun in age and size, and look in those directions with more sensitivity and the ability to detect maybe more complex signals.
The targeted search will look repeatedly and at different frequencies at 800 nearby stars for about 1,000 seconds each. NASA researchers hope to use the world's great radio antennas in their search. They say antennas in the southern hemisphere are also needed, such as the one at Goldstone's sister station in Australia. Most of the stars in the Milky Way are best observable only from the southern hemisphere, but so far only a few sporadic searches have been made from there. The realities of contemporary SETI are quite different from the fantasy seen in the movies. Most scientists believe alien visits are unlikely, and a dialogue would take too long. So a one-way message via radio is the best we can hope for.
But you know, it isn't a complete tragedy if we just receive a message and don't have time to talk back. I've received lots of one-way messages of great significance from Socrates and Shakespeare, Charles Dickens and Emily Dickinson, from Gilbert and Sullivan, from every author and poet and composer and thinker now in the human past. But in SETI, it's our future that might be speaking to us.
That I think this enterprise can best be understood as a kind of exercise in the archaeology of the future. We're well aware of the archaeology of the past. We find a site, a tumulus or a ruin, and we take a spade and we dig into the ground, and if you're lucky, you discover Ur of the Chaldees or something marvelous. Now, we never thought that we could examine the same thing in reverse time, but in fact, in a way, we can. We know that it's possible that somebody who wants to do it will bring us in. Of course, it is their past, but our future, which we're investigating to some degree. Even though they're made of different chemistry, even though they've never seen our star, even though they have nothing biological in common with us, they have, if they have got radio astronomy, if they have the kind of technology we're imagining, have very much in common with us the manufacture of a culture, the development of a culture which is unmatched in all the 10 billion species or more that have come to the face of the earth. So that's the story, and maybe the spade will turn up, luckily, a good site one day. We hope it will. It's just a question of being patient. When you got the spade and you know the future is there, it seems very wrong not to dig.
Hello?
For a transcript of this program, send $4 to Nova, Box 322, Boston, Massachusetts, 02134. Please be sure to include the show title. To purchase film or video copies of this program for educational use, call toll-free 1-800-621-2131. In Illinois or Alaska, call Collect, 312-940-1260. This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for NOVA is provided by this station and other public television stations nationwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And the Johnson & Johnson family of companies, supplying health care products worldwide.